In this video, I want to spend more time talking about sampling, specifically related to the theory, how we can draw random samples, and what is a sampling distribution. The reason we are going to spend some time here is because understanding sampling and sampling distributions is really critical to understanding statistical inference. This is going to become particularly helpful when we go to understand p-values and confidence intervals as we analyze regression results. Let's start with why do we sample? We sample for three main reasons. First, selecting a sample is less time-consuming and less costly than selecting every available item in the population of interest. An example where we actually do select every item in the population is the US Census. In that case, the US government hires a large number of temporary employees, trains them, and deploys them to go out and survey all US residents. Obviously, this is an enormous undertaking to gather some basic information about the US population. It's far too large for most companies to actively undertake just on their own. Instead, what they do is they select a sample of individuals from the US and use information about that sample to infer something about the larger population. It saves them time and it saves them a lot of money. Second, an analysis of a sample is less cumbersome and more practical than an analysis of the entire population. Here we are getting down to some big data concerns. The larger our dataset gets, the more difficult it becomes to analyze the entire dataset. By analyzing just a sample, we can frequently save ourselves a lot of time on the analysis and still obtain pretty accurate results. Finally, a sample can be more insightful when it allows depth of coverage and key perspectives. This is one point where the US Census really suffers. It's well known that the US Census underrepresents people that don't have homes, people that don't have phone numbers, and basically anyone who is hard to reach. By establishing a sample, we can make a greater effort and put more resources to go out and reach these individuals that are hard to reach. Then we make sure that we get responses from them and therefore arrive at more valid conclusions and more accurately represent the entire population. So how do we go about actually drawing a sample? First, we have to select the method of sampling. There are several methods for sampling. There are non-probability samples, which are either judgment or convenience samples. These frequently come into play in business with things like focus group or expert panels where we don't necessarily need a sample that represents everyone in the population, but we rather are looking for a specific type of expertise. Then we have probability samples, and then within probability sample we have simple random samples, which are going to be the most common ones and the ideal ones that we want to use. There are also systematic samples. For instance, we systematically test every 10th product in a production line. So we let 9 products go, and then we test the 10th product, and then we let another 9 go, and then we test the 20th product, and so on and so forth. Then there are some other sampling techniques that allow us to differently weight the results based on populations that may be difficult to reach and are underrepresented. These are either stratified sample or cluster samples. One of the most important things to understand about samples is the concept of a sampling distribution. We are going to spend a good amount of time here because it is really critical to understanding analytics, statistical inference, and really a lot of the assumptions behind regression. A sampling distribution is a distribution of all the possible values of a sample statistic, like the sample mean, for instance, for a given sample size selected from the population. Let's take an example. Suppose we have a sample of 50 students regarding their average GPA. you could actually obtain many different samples of 50 students and compute a different mean for each of the sample. The sampling distribution is a distribution of the mean GPA for all possible samples of 50 students. So it means you take 50 students, compute the mean, and then you take another 50 students and compute the means, and the mean will change a bit each time, and you look at the distribution of these means. Now let's turn to a more concrete example of a sampling distribution. Assume there is a population of size 4. That's a very small population. There are 4 people, and we are interested in the age of these individuals. The values for their age are 18, 20, 22, and 24 years. Now let's consider a sample size of 2. And so we take a look at what the distribution of possible samples of size 2 looks like. Well, we can fully enumerate all possible samples since there is only 2 observations within each sample. So if we look at the table on the left, we could start by drawing an individual that was 18, that's the first row. And then since we are sampling with replacement, we could draw again that same individual that is 18, and we will be in the first row, first column, and we have a sample that says 18 and 18. We can also start by drawing this individual that is 18 and then draw an individual that is 20 instead, and then we will have the sample 18, 20, and so on and so forth. Note that in this table, every single result is equally likely. We can then calculate the mean for all of these samples, and that's what we show on the right table. So if you draw the 18-year-old person twice, then the mean is of course 18. If you draw the 18-year-old first and then the 20-year-old person, the mean is 19, which is the first row and second column. And then you can see we have the different means for all the possible samples in the right table. So these are all the 16 possible samples that we could get from a population of 4 with a sample size of 2. Let's look at what the sampling distribution for the mean looks like. There are 16 sample means, so we can plot that sampling distribution just as we did with the probability distributions video. That's what we have in the plot on the right, and you can see that it is symmetric. It's not really bell-shaped, so it's not quite a normal distribution yet. That's because the sample size is very small, only 2 individuals, and the population is also small, 4 individuals. But you can see that it is approaching something resembling a normal distribution. Importantly, the sampling distribution of the mean is very different from the population distribution of ages. The sampling distribution on the left is approaching a normal distribution with a mean of 21 and a standard deviation of 1.58. The most likely outcome is that the sample will have a mean of 21. The second most likely outcomes are that the sample will have a mean of 20 or 22. Again, this is simply interpreting the probability distribution as we did in the probability distributions table. If we turn our attention over to the population distribution, we can see that the mean is still 21, but the standard deviation is now 2.2. Importantly, if we draw each individual, or if we draw from the population one at a time, getting an individual that is 18, 20, 22, or 24 are all equally likely outcomes with a probability of 0.25. While the mean is 21, it is actually impossible to draw a single person from this population that has an age of 21. Whereas for the sampling distribution of means, the most likely outcome was 21. Now let's talk about some of the theoretical underpinnings behind sampling distributions. One measure of variability of a sampling distribution for a mean is the standard error of the mean. In the case of random samples, this is simply the standard deviation of the population, if we know it, divided by the square root of n, which is the sample size. For normally distributed populations, the mean of the sampling distribution will be equal to the mean of the population. Importantly, and this is probably the most important thing I want you to take away, is the effect of increasing the sample size on the sampling distribution, which is shown in the plot below. When you increase the sample size, the mean stays the same. However, the standard deviation decreases significantly. The larger the sample size, the smaller the standard error of the mean with regard to the sampling distribution. So if we draw large samples, we are more likely to get a sample mean that is close to the true population mean.